Here's a video to help you understand the halogens as leaving groups. The halogens are in group 7A at the far right of the periodic table. Fluorine, chlorine, bromine, and iodine are the most common ones. And they often appear as leaving groups. Leaving groups are either an atom or often a group of atoms that leave or pop off of a molecule. So they can just come off of a molecule. They do that by taking the electrons that were tying them in a bond to the molecule and ripping them off and taking them for themselves. So when the leaving groups come off of molecules, they have those electrons on them. Those electrons then give that leaving group a negative charge often, or at least the electron density that was being shared in the bond between the leaving group and the carbon chain goes completely onto the leaving group. And so the leaving group gets the negative charge that comes with those electrons. If the leaving group is just one atom, then its size makes a big difference in how it can stabilize that negative charge. If the atom is very small, like on the left here, then it has to stuff that negative charge inside of that very small area. And so the negative charge is very concentrated, and it repels itself a lot, and it's very unstable on the left. Compare that with the atom on the right. If the atom is very large, then it can spread that negative charge out over its enormous volume, and that will stabilize that negative charge by diluting it in space. So if you have a single atom acting as a leaving group, the larger atom will be more stable. Because it's more stable after it leaves, those larger atoms tend to leave molecules more easily and more often. If you have just a single atom coming off of your carbon chain, a larger atom will act as a better leaving group. So let's look at the halogens in group 7A and see how they change as you go across this periodic table. Now, the atoms get bigger as you go to the left and as you go down. So as we go down in this column on the periodic table, we'll see the halogens gradually get bigger. Those bigger atoms mean that they're going to behave as better leaving groups. So if you look at fluorine at the top right, the top of group 7A, let's look at an example molecule, the molecule I-fluoropropane. The skeletal structure for that would look something like this. And let's visualize that in 3 dimensions with all the molecule knocking around. Notice how the fluorine here is relatively small. It's almost the size of a hydrogen. It's a little bigger. Because it's so small, it would not be a good leaving group. If it tried to come off the molecule, it would be like that atom on the left was in the drawing earlier, with the negative charge stuffed in a small space in a very concentrated way. And so the size of fluorine there is preventing it from being a good leaving group as an atom. Compare that with what happens with chlorine. Now, as you go down in a column, atoms get bigger. And so if we get that same molecule, but we replace it with chlorine, so we have I-chloropropane, whose skeletal structure would look something like this, that chlorine is going to be larger. Quite a bit larger. A chlorine atom is a little bit bigger than a methyl group. And so here, because chlorine's bigger, it can take the electrons in the bond into itself and leave the molecule because it'll spread those electrons over its enormous volume. It'll spread the negative charge over its enormous volume, and that dilutes that charge in space and so stabilizes it. Compare that again with what happens with bromine. As you go down in a column on the periodic table, atoms get bigger. And so bromine is going to be even bigger than chlorine. Let's look at an example molecule, I-bromopropane. So the same thing, we're just replacing the chlorine with the bromine. You can see the skeletal structure here. The bromine is even bigger. It's starting to dominate the whole molecule. The bromine atom is enormous. That means it's going to be a good leaving group. It can leave the molecule, take the electrons that were in the bond, holding it onto the molecule, take those onto itself, spread them out over its enormous volume, and dilute them even more in space. That stabilizes the negative charge, or the electron density that ends up going onto that bromine. The case gets even more pronounced with iodine. As you go down in a column, atoms get bigger. And if a leaving group is just one atom, the size of the atom determines how good of a leaving group it's going to be, how stable it can get after it leaves the molecule. So iodine, let's look at an example molecule, I-iodopropane. And so the skeletal structure looks like this. So it's just like the other ones, but with an iodine as the leaving group. You can see the iodine is enormous. It's almost bigger than the whole carbon chain altogether. And so iodine is an amazing leaving group. It pops off of molecules very, very easily and very, very quickly. Once it comes off of that carbon chain, it rips the electrons that were in the bond holding it on. It steals them for itself, and it can spread them out over an enormous volume. That dilutes the negative charge that comes with those electrons and stabilizes it by diluting it in space. If anything, iodine is such a good leaving group that sometimes it can be inconvenient to use because the atom is so large that it will pop off of molecules very easily. And so it's not as selective. It tends to take some selectivity away from your reactions. It won't take much to push that iodine off of a molecule. So the most common leaving groups are chlorine and bromine. Those are good leaving groups because they're big atoms, but you still have some selectivity with them. Nonetheless, iodine can be used. Let's compare all four of those. So you have from left to right fluorine, chlorine, bromine, and iodine. And here you can see the relative sizes of those atoms. The bigger the atom, if it's a single atom acting as a leaving group, the bigger the atom, the better the leaving group.